BP. So triangle BOP is congruent to triangle AOP. And that implies that the corresponding parts are congruent. So corresponding parts of congruent triangles are congruent. So BP must be equal to AP. And so BP plus AP must be the length of that side, which is 1. So AP, twice AP must be 1, so AP must be a half. Which, you know, you might have jumped to that conclusion, but it's helpful to carefully lay out the wheres and why-fors. So finally here, part C, the segment AA prime is one side of a regular polygon. Oh, we didn't get the other side, did we? So what's this side here? Well, this is a right triangle, right? So we can apply Pythagoras' theorem. Now, what would Pythagoras' theorem say about OP squared plus AP squared? It's going to be the hypotenuse OA squared. And we know that, well, OP is the unknown. We know that AP has length 1/2, and OA is the radius of our unit circle, which is 1. I didn't label that, did I? It's length 1, right? And so OP squared must be 1 minus 1/4, which is 3/4, which means that OP is square root of 3 over 2, right? And there's that familiar trig number, right, which is approximately 0.866 or 866 thousandths. One of those well-known trig numbers, right? So finally, AA prime is the chord of the circle, right? That's this length here. And it's one side of a regular polygon which can be inscribed in a circle with radii OA and OA prime, right? So if I were to, bisect this and draw each of these, they would all be the same. That would be a dodecahedron. Sorry, a dodecagon. How many sides does have I given it away? Yeah, that's pretty easy, isn't it? Okay, but try to lay out your reasoning carefully, right? It's easy just to sort of put down an answer without supporting it. So what I'm looking for is the support for your answer. And let's just briefly introduce this last part, and then we'll have the project for task 2, huh? Greek geometers and techniques had techniques to determine the lengths of the sides of certain irregular polygons, as in the task above, but not others. The length of the regular heptagon, task 4, could only be approximated. Yeah. Given the circle, the length of the side of a regular heptagon, right? Given a circle with center O and any 2 radii, and by the way, so we're able to deduce this side and this side, so we'll be able to compute that and that. So from that, we could then say, well, this is also a right triangle, so we can get the length of AA prime. That's not what they're after here, but that would be doable. In any case, the line segment AA prime is called the chord corresponding to angle AOA prime, right? So this central angle, 30 degrees, subtends a chord AA prime on the circumference of the circle, right? And that's one side of a regular dodecagon. It's not surprising to learn Hipparchus was reported to have prepared a table of central angles and their corresponding chords for use by astronomers and astrologers. Well, I guess they were the same thing in those days, right? Even Kepler was an astrologer in the years later. Thousands of years later? Anyway, we have independent reports from Vettius Valens, a contemporary of Ptolemy, and author of the astrological work entitled Anthology, and also from Theon of Alexandria in his commentary on the Almagest, that Hipparchus had indeed prepared such a table. Unfortunately, no copy of this work of Hipparchus survives today. However, a number of scholars in recent years have proposed a likely reconstruction of this table. Here we see, so what are we looking at here? Arcs 730, is that a sexagesimal number? What would that be if it was a sexagesimal number? Well, 7 times 60 is 420. So add 30 to 420, you've got 450. What are we looking at here? This is a reconstruction of some sort, huh? Chords 730, so so we have the arcs and the corresponding chords in these two columns, and 730 corresponds to 730. Well, let's see if we have some explanation of these. So how are we to make sense of the numbers in this table? First, because this is the work of a Greek astronomer known to have been influenced by the tradition of Babylonian science, we should interpret the numbers that appear in the table in the bracket notation as we have for sexagesimal numbers. Thus, it seems clear that the values in the arcs column are measuring the arcs along a circle. Really? A 450-degree arc, that would be more than 360 degrees. Huh. Or equivalently, angles at the center of the circle, since they end at the telling value 180, 0. Oh, okay, so maybe that's degrees and minutes? Would that make sense? 60 or so degrees, since what look like degree measures appear in the position of the digit to the left of the units digit. This would be the units digit, and this would be what, degrees? Oh. Okay, so let's read this last sentence. It seems clear that the values in the arcs column are measuring arcs along a circle, or equivalently angles at the center of the circle, since they